an industrial view now to to a more academic one. I'm happy to welcome Josep Vidal here from us in this workshop. He's the leader of the Freedom Project, actually, which is a project running in parallel to BeFEMTO, doing complementary issues related to femtocell design. He's a professor at UPC with his group. He's published loads of papers, loads of books, pretty well-known person with a background in signal processing, cooperative communications, information theory, etc., etc. So I'm sure he will give us a great overview what is hot and what is not in the academic development of femtocell designs. Thank you, Giuseppe.
Thank you. I'd like to start thanking Misha and Thierry for inviting us to present what is going to be a framework on the research activities on femtocells and also the activities of the Project Freedom. So I'll try to do a complementary perspective of femtocells as compared to the presentation of Thierry. And my presentation will be basically focused on two aspects. First, why small cells are needed in the light of new communication services and new attitudes of subscribers, and what are the technical challenges in femtocells. And of course, this is kind of a very open issue. What are these technical challenges? This is very debatable. Some of you might consider that what I will explain here are pretty much new stuff, and some others might think that there is some missing parts in my presentation, some aspects that you are dealing in your own activity, in your own research, on your own work for your PhD. So I would like you to interrupt me anytime or in the end to make questions, to pose questions and open a debate of what do you think that are new trends or new challenges that I didn't consider in my presentation here. So first of all, why these small cells are needed? I think that this is something that Thierry has mentioned. We know that we have all these hungry bandwidth eater terminals, all of us, that are generating a lot of traffic, but it's not only the traffic per device that is important, it's also the high penetration in the market. So we have here a few numbers of what is the penetration in Europe in different countries, but most important is that the growth of this penetration of smartphones and dongles is growing yearly around 30% in Europe. This translates into a mobile data traffic that is increasing exponentially, and here are a few figures that I'm sure most of you already know. But it's not only that these devices are in the market, it's that our habits have also changed in terms of what are our expectations from the network. If we look at the requirements of the subscribers a few years ago, what we demanded from a mobile network, okay, what we demanded is basic coverage. Like we would like to have good coverage for voice services, maybe not in all places, but for sure good coverage around the base station. And that was mainly our requirement that we're evolving over time, because we want now to have data coverage, and data coverage that has reasonable service almost everywhere in the cell. We don't want to have gaps of coverage, and we assume that we have good voice services, and that is for granted. Now, with the advent of these new terminals, now we are getting more and more exigent in our demands to the mobile operator. We want to have data coverage everywhere, not to have coverage holes, And in fact, what is happening is that the demands of traffic are exceeding the capacity of the access network, of the conventional access network that is based on macro base stations deployed over rooftops or in high positions. That is very big equipment with high transmitted power. And we have this impossibility of increasing the capacity with more macro cells because of the very expensive CAPEX and OPEX associated to the deployment of macro base stations. So let me have a look, a more technical look into the why do we need small cells, and this is an easy way to start by resorting to the famous Shannon formula, right? That is telling us that the maximum transmission rate is related to the bandwidth that we allocate to our transmission, and also to the path loss or the effects of the channel, of the transmission channel, on the transmission signal. And we all know that when we have obstacles in our cell, then we experience like a loss of performance in our transmission. And the presence of obstacles is more likely as the macro base station is away from the user terminal. So this transmission is affected by, of course, the propagation channel, something that you know from undergrad courses. And the propagation channel can be characterized by mainly three terms. One is path loss, right? That decays in a way that is exponential with the distance. We have also shadowing, that is the effect due by obstacles and occluding the transmission from the reception. And also we have fast fading, which is related to the reception of multiple paths, multiple signals reflected on the obstacles of the scenario or the different items in the scenario, and that are generating deep fadings on the received signal over distance. So what has been the conventional, okay, before going to that, there is another aspect that is important in wireless communication, is interference, right? And interference is important as we have multiple cells, and then we need to have in mind that the allocation of resources between different cells need to be such that outage service to terminals is not caused by too much interference. And often this is achieved at the expenses of reducing in spectral efficiency by just splitting the band or the resources over space, over different cells. Now, what are the possible solutions to these two effects, like the deleterious effect of the channel and also to the interference? Well, one approach was, it's now conventional, it's to use multiple antennas at the transmitter and the receiver, and this was the so-called famous MIMO systems. And MIMO systems have the advantage that you can transform this Shannon formula in a way that scales with a minimum number of antennas at the transmitter and the receiver, at least at high signal-to-noise ratio. And you have some kind of possibility of canceling of reducing the impact of interference by canceling interference when you have multiple antennas, either at the base station or at the mobile. However, the main drawback is that it is not robust to shadowing or path loss. We know that the MIMO system can take advantage of the dispersion of the channel, so kind of can take advantage of the multipath fading, but not from the shadowing of or the path loss. And this is one of the reasons that to resort to small cells. And this observation is also sustained from the experience, from the history in the development of wireless systems. We know from Cooper's law, I guess you all know who's Cooper. Cooper is the chief technical officer of Motorola, one of the inventors of the mobile telephone. He observed that the number of possible radio communications over the world has been doubling every 30 months over the last 100 years, since Marconi times. And this increase has been caused by different effects. One is the achievability or the availability of more spectrum, and this more spectrum is has been increasing the capacity in a factor of 25. Well, I think that I said 100 years, but these figures are taken for the increase of capacity in the last, let's say, 60 years. So another factor that is coming into our help with the increase of capacity is the frequency division. It's like doing a more advanced or more enhanced multiple access scheme. Then we have capacity increases on a factor of 5. Then we got also a factor of 5 from the improvement of modulation coding schemes, and amazingly a factor of 1600 by just doing a spectrum reuse. That is, by reducing the size of the cells and by increasing the reuse of the frequency bands. So we need small cells just to combat this effect of path loss, and we need therefore a more aggressive interference control also if we want to achieve a large capacity. Now this is from the side of the let's say the capacity, the achievable capacity from a wireless communication system. What is the other aspect that is interesting for us, and this is what I start to mention in my presentation, is that the traffic is also affecting the design of wireless systems in the sense that we need to go into small cells. And the characteristic of the traffic can be stated in this way. More than 60% of the mobile traffic, which is mainly voice, is generated in indoor environments, in homes and offices. And this increase of the traffic reduces, of course, the cell coverage. And if the traffic per square kilometer is increasing, then we need to reduce the cell size. If we have smaller cells and a larger spatial reuse of the radio sources, and this is something that is being considered now in 4G standards. However, 4G standards, as you know, are going into higher frequencies. They are considering 2.6 gigahertz bands, although you know that there is also this digital dividend that will introduce low attenuation bands into the market of mobile communication systems. But if we want to have access to this 2.6 gigahertz band, then we need to know that this high frequency band have higher built-in penetration losses. So we will have poor coverage, especially in the situations, especially in the positions where most of the traffic is being generated, that is at home or at the offices. So these previous statements imply the necessity of an increased number of base stations. That means that we need to reduce cells to provide higher capacity per square kilometer, but we need also to reduce cells because of the use of higher frequencies. then everything is going against the economics, in the sense that providing broadband coverage for indoor scenarios would require an increase in the density of base stations, but to do that with traditional deployments entail very high cost, both in CapEx and OpEx. You all know how big are base stations, big equipments, big in terms of and expensive in terms of investment, of capitalization, and also for the operation of these devices. Not to mention the fact that these are very much energy inefficient machines, in the sense that they need a lot of cooling, which in principle would not be needed for small cell base stations. So this is how new paradigms in the definition of wireless communication system have arisen. So they have gone from the conventional macro base station user equipment coverage over a certain cell towards what I consider here 4 different paradigms in small cells. One is the remote radio heads, the presence of antennas which are spread over the cell. They do not have like intelligence. They are coordinated by a macro base station or a node B in LTE terminology. And this macro base station is connected to these remote radio heads by dedicated backhauls, fiber optics that are able to transmit samples at a very high rate. Another of the paradigms is the picocell, which is mainly a base station which is connected to the core network of the operator. It's not anymore like the remote radio head. Is not. The remote radio heads are connected to node Bs, but these picocells are mainly node Bs, which are connected to the core network and have lower power, lower transmitted power than the macro base stations. These picocells still require, as for the macro base stations, the planning of the network, in the sense that they need to be installed in precise positions, and the frequency allocation or bandwidth allocation needs to be precisely done by the operator. Another of the paradigms is the presence of relays, relay terminals. As compared to remote radio heads, or as compared to picocells, I would say, these relay terminals are, well, they have, in a way, they have like similarities to remote radio heads, in the sense that they are coordinated by a macro base station or an node B. But unlike unlike picocells, they do not have a backhaul which is a wired backhaul. The backhaul is usually supposed to be a radio backhaul, and most often an in-band radio backhaul. That is, the bandwidth used for communication between the macro base station and the relay terminal is the same band as used for the association or the access from the user terminal to the relay terminal. So if this relay communication is done in band, then it needs to it requires coordinated radio resource management for the radio backhaul and also for the access. And the fourth paradigm is the femtocell. The femtocell is a small base station that is usually giving coverage to very small reduced cells. They have low transmitted power as compared to picocells, as compared to relays and remote radio heads. They are usually connected to the core network through an ADSL on an ISP, Internet Service Provider line, be it XDSL or fiber, whichever other technology. And they have a very interesting feature, which is that these femtocells, these femto base stations, are devised in a way that they can self-configure each other. Unlike relays, unlike remote radio heads, and unlike picocells. So they can configure, they can sense what is the environment, they can self-organize, use the bands in a smart way to have some capacity of self-healing, and this is the main difference as compared to the rest of technologies. So this is why they are interesting for indoor coverage, but also the operators are interested in like having outdoor deployment of femtocells because of this facility in terms of network configuration. Yes?
Can you highlight the difference between RRS and the picocell?
Between?
RRS?
Remote radio heads?
Yes.
And picocells? Right. Yeah, picocells are mainly base stations. They have lower power base stations. They have lower power. Whereas remote radio heads are not base station itself. They are just equipments that are containing the radio devices and the antennas. They don't have baseband processing.
They just amplify repeaters.
Yes.
They don't decode and forward. They just amplify and forward.
It is like imagine that it's kind of a distributed base station, right? So the intelligence is centralized and the signal processing is centralized, but the antennas are spread over the cell, right? And to have this, the feed of these antennas is done through a fiber. Yeah, and it needs to be high rate communication link in here because it needs to transmit samples, like signal samples. So the benefits of femtocell-based deployments are like this. They provide service to small groups. They have the ability of offloading the macro base station so that more radio resources are available to outdoor users. They can enhance indoor coverage. They communicate to the core network through inexpensive DSL backhaul. Right? DSL backhaul is almost available everywhere right now, so femtocells are becoming more and more interesting for operators to reduce the expenses of deployment. Femtos and macro base stations usually share a license band. They can split it or not, but they are usually using the same license band as owned by the operator. They have very interesting properties in terms of energy consumption. I think that they can be tagged as the technology, as the key technology for energy, for green communications in the future. And they offer new opportunities for tariff plans. So new opportunities for interesting, that are interesting for subscribers, but also new services that may arise from the pervasive deployment of macro base stations into homes. And I think that in the future there will be more and more applications related to this pervasive nature of femto base stations. Now we all know about these location-based services, but in the future I guess there will be more and more services related. And this is why these small cell deployments have been recognized recently as key technologies in LTE, and also they appear in any white paper that you may find around. For instance, I included here reference to the white paper of Networks European Technology Platform, where in the 5 year, 10 years, and 15 years perspective, they are including all these technologies related to relays, to femtos, and to remote radio heads. Now this concludes the first part of my presentation. I don't know if you have questions about. I hope you all are convinced that we need small cells by now. So let us see what are the technical challenges in femtocells, and I will cover a few of the items that have been, in fact, covered by Freedom Project and also by BeFEMTO project. And those are related to the scenarios, to the channel characterization. We might think that everything is known already in characterization in the channel and the models, but I'll tell you something about that. I want to mention about interference management, about the complementarity of relays and femtos, some multiple access aspects. I'll mention something about mobility management and also about routing. So let me go first to the scenarios. So we all know about scenarios and for deployment of femtos. We have this corporate, dense urban, where a company might decide to deploy femtocells within their premises, and all these femtos are connected to the IP network of the company. But we have also interest in outdoor rural deployment, because femtocells have this self-organizing and self-healing capability, and also low power consumption that makes them ideal to be deployed in rural areas, like in many wide rural areas in South America or Asia. But by far, what is more being considered is the deployment in a residential area. Well, femtocells are deployed at home and connected through the DSL, which is more and more quality characteristics, and it's going to be better and better in the future. So once we have these femtos deployed, what is required for coverage prediction? I mentioned that the femtocells have this self-organizing capability, but the operators are still interested in knowing what is going to be the coverage prediction if we deploy these femtocells in the most rewarding scenario, which are the urban scenarios, and especially the residential scenarios. So we all know that there are a lot of models for propagation, but there are a few that are still needed to be precisely defined for femto coverage, for femto deployment. We need to know more about the stochastic channel models, site-specific path loss models, for instance, reflectivity on the windows, diffusion, and diffraction models for windows. It is important to enhance some of the channel models that had been generated in WINR. We also need to know more about indoor to outdoor path loss models, but also to indoor, outdoor, and indoor path loss models. Another aspect which is important is the impact of human activity. We all know that femtos are thought to be placed at a level which is around 1 meter or 2 meters high. Right? And in those positions, the impact of the occlusion of the signal by the human activity is important. So we need to know models about this time varying component of the channel. And these are usually, and this is the methodology that we have used in the Freedom Project. We have to resort usually to models generated by ray tracing. I am showing you here a plot where there are a few obstacles in a certain room, which are shown here by red boxes, and a model of a person, which is here a cylindric person, here right in the middle, which is occluding the propagation of the signal. And this is the model that we have been using in the Freedom Project to generate a more advanced shadowing model associated to the movement of the person.
Just one question. Do there exist some models on the user movement inside the buildings? Some more abstract things than just, you're going back to ray tracing essentially, which is very heavy processing every time you want to do some planning. So is there no model available where you could actually use some statistical information just to build it into the capacity stuff?
Well, I can tell you what we have done here in Freedom. It's like to use ray tracing to generate the statistical models.
Okay, so you have developed.
So we have a model for the movement of the cylinder, which is basically a random walk model, and then we have generated statistical models based on the observations from the ray tracing.
Okay. So do you take into account opening and closing doors and things like these, which I observe personally at home very much. So if the doors are closed, my Wi-Fi is very lousy, and if doors open, it's much better. So that, I think, has a bigger impact than a person walking through.
That's a good point.
Yeah. Right.
We don't have considered that anyway, but it's a good point. Let's have a look at the next item, which is interference management. We want that these femtocells have this self-organizing capability. So it is important, therefore, that the radio resources are distributed or are allocated in a distributed way. Also having in mind that the deployment of femtos will be more and more dense in the future. And this dense deployment requires scalable distributed solutions that are not easily handled by centralized radio resource management, by having gateways that allocate resources to the different femtos. Also, the provision of quality of service, that is one of the key items in LTE as compared to Wi-Fi, as you know, implies a certain degree of coordination between the femtos. Like the femtos needs to exchange a certain number of parameters so that the radio resource allocation is done in a coordinated way. Like we cannot tolerate that there are femtos that are working in a greedy way, like consuming all the resources, whereas others are in outage. So the existence of the X2 interface as defined in LTE, which is so far defined for communication between the macro base station and the femtos, needs to be extended to communication between femtos. And in this respect, in the Freedom Project, we have made some contributions to LTE in rank 1 and in rank 3. Also, the fact that these femtos might work in the paired or an unpaired bands imply that the requirements in synchronization is different. For the TDD mode, for the TDD band, there is some need of synchronization between femtos, which is not easily achievable by using network-based synchronization protocols like NTP or PTP. As you know, NTP is more distributed protocol, whereas PTP requires some gateway that is generating the synchronization. Some solutions are being envisioned in LTE, like over-the-air communication between femtos, but this is still something that is not very mature at the standard so far. When talking about interference management, we don't have to forget about the presence of the macro base stations. So these macro base stations will share band with the femtos, and there are also different solutions associated to the management of these macro to femto interference. One is static allocation, like thinking of the macro base stations operating in the fractional frequency reuse patterns as defined in LTE. And on top of that, we are overlaying femtos that, depending on its position on the cell, they could use different sub-bands of the bands allocated to the macro base stations. Or we can envision of another approach, which is more dynamic approach for the allocation of resources, by assuming that the macro base stations are as another entity, as another femto base stations, let's put it in this way, in the allocation of resources. So the information that they exchanged through the X2 interface to coordinate resources is done between the macro base station and between the femtos in a way that can be more hierarchical. That means that the macro base station could have higher priority than the femtos, but they could anyways work on the same, under the same let's call it algorithm for the allocation of resources. And also for the interference management, we need to have in mind what is the backhaul quality. And we need to have in mind the backhaul quality, the DSL or the fiber that is connected to our femtos, in two respects. One is that the DSL backhaul will have to support the coordination of these allocated resources, allocated radio resources, and then this DSL backhaul is subject to, for instance, delays, is subject to packet losses, and this might impair the coordination of resources between the femtos. Another respect, depending on the DSL grade, then we might think of femtos that are providing more service or less services. It can be easily thought in the way that if we have a low bandwidth DSL, then the transmitted power on the radio side should be lower because we are demanding, or we have less demands from the backhaul, from the DSL backhaul. Also, depending on the quality of the DSL, we could think of doing like an improved interference coordination by doing cooperation in a way as it has been recently proposed in LTE, using coordinated multipoint or distributed MIMO, like many femtos having or sharing their antennas in a pool of antennas that transmitting information simultaneously to many users. I will talk about that a little later. Also, DSL asymmetry plays a role. DSL has higher bandwidth in the downlink than in the uplink, and this needs to be taken into account in the allocation of resources for the uplink and the downlink. Therefore, overall, we need reliable models for this backhaul, and this is something that we have done in the Freedom project, and this is information that is available for you all at the Freedom website, whose link I will show you later. So these models for the backhaul require, first of all, to define an architecture for the backhaul, starting from the modem associated to the femto, up to the internet-based core network of the operator. And the models need to include the bandwidth, the delay, the packet losses on this backhaul, and also the time coherence of all these parameters. And this model needs to be incorporated into the optimization algorithm for the resource allocation. Now, depending on the quality of the DSL backhaul, the management can be conditioned by the information that can be exchanged between the femtos. Then imagine that we have a backhaul that is not reliable at all, and you cannot trust on the exchange of coordination messages between the femtos. Then in that case, each femto is like kind of alone and has to trust on its own sensing of the status of the environment, or what is the occupation of the different bands. Like this is kind of a situation which is related to, or similar to the cognitive radio, where you would like to either cancel interference. You have maybe the possibility to cancel interference when you have multiple antennas, or you have the possibility to do successive cancellation scheme at the receiver. But otherwise, you need to test or to check if the transmission band is occupied or not, and then to do a robust selection of the modulation coding scheme to be transmitted, and possibly also of the transmitted power. Then imagine that a second situation where the backhaul is more reliable, and then you can exchange control plane information. And then in that case, you can think of doing a coordinated allocation of resources, as I have been talking before, and resort to distributed algorithms like a game theory or algorithms based on pattern recognition. Yes?
So for the interference, which one is more dominant? Is from the macro to femto, femto to femto, or like depends on the case?
That's a good question, because it all depends. It all depends on, maybe on the position of the femtos, on how you deploy the femtos, if close to windows or very inside the home. I would say that for very dense deployment of femtos, then femtos to femtos are more interfered to each other. Otherwise, the interference is possibly more important from the macro base station. I would say that it depends on the position, but also on the density of the deployment. But in this respect, I think that it is important that when designing distributed radio resource management system, then both base station and the femtos are involved. And then a third aspect of the quality of the backhaul, which is a third situation in the quality of the backhaul, is that we have a very high quality backhaul, and then we can think of exchange of information between femtos and macros at the data plane. Then we can think of cooperation, doing joint precoding, like in network MIMO, cooperative multi-point systems, which also requires tight synchronization depending on what is the strategy that is used for cooperation. Now, interference coordination basically provides two different solutions. One is that femtos are serving users simultaneously, like in this situation here, where we have close distance between the femto and the associated user equipment, and these are far apart each other, so that the interference between them is small, is a very tiny amount of interference, so they can transmit simultaneously, possibly with their coordinated transmission power. But another situation is maybe like this, where you have users that are close to each other, and then the transmissions from the base stations to each user interfere a lot, and then the best solution is possibly to orthogonalize resources between them. Now, each one or the other solution needs to be reached by applying distributed algorithm. Usually when you apply game theory-based techniques, then one solution or the other is reached depending on the position. And this is precisely what I mean when I say that our algorithm needs to be self-organizing. Is that we do not need to know exactly what is the position of the femtos or the position of the users, but our radio resource management is automatically converging to either one solution or the other, depending on the situation, on the propagation, on the interference. Yes.
Sorry if I missed it. Are we discussing the downlink or the uplink there?
Yes, these examples are for the downlink, but they could also be thought for the uplink. Now, when using game theory based techniques, these can be defined in a competitive way, like each one is acting in a greedy way. But if we think of this game theory with a more cooperative perspective, where every femto is exchanging some kind of parameters through the X2 interface, as I mentioned before, then this provides the ability of giving to every communication some kind of quality of service. Criteria for the definition of this radio resource allocation can be many. In particular, we can think of to optimize a maximum or to maximize the weighted sum rate of the different users. Game theory provides the framework to do that, to maximize the weighted sum rate and give at the same time a certain priority through this mu parameter to the different users in the different femtos. I brought it here three femto deployments, excuse me, because this plot is kind of different as compared to the previous ones, but we should think of this terminal as a macro base station giving service to these two users. This is another macro base station giving service to these two users, and each one is optimizing in a coordinated, non-greedy way the parameters of its transmission with the neighbor femto base stations. And this can be done through this maximization of this criteria, but at the same time we need to impose certain restrictions, like in the sum power per femto access point per femto base station, if this femto is giving service to multiple users, but also a certain restriction on the backhaul rate constraint, right? So that we cannot give more bits per second to these users than the bits per second that are arriving through the backhaul. This is one of the criteria. Another criterion is minimum sum power. That is, if we want to provide the users with a certain bit rate, then we are interested in minimizing the transmission power so that not to affect too much the other users. So in principle, we might think of this criteria is more suited for let's say best effort traffic, whereas this criteria is more suited for fixed data rate traffic. Yes.
This optimization is a non-convex optimization problem, right?
Yes.
So do you develop tools to also solve this kind of an optimization problem, or is it just a brute force,
No.
some
No, game theory provides the way to solve this non-convex problem in a distributed way, and of course you are not getting the optimum,
yeah,
right?
That's what
But at least you are getting some distributed solution,
it might be locally optimal.
you are luckily, optimal. But you can get close to the optimum. let's put it another way. You want to optimize this criterion, which you know it is not convex, but you can operate with this expression so that you can define a game which is completely non-cooperative game, or a game which is partly cooperative, right? When the game is non-cooperative, you get an optimum which is farther away from the, or you get a maximum which is farther away from the optimum. When it is cooperative, that is when the femtos exchange some kind of parameters, you get closer to the optimum.
Okay.
But in any case, you cannot be sure that.
Sure.
Yeah.
Thanks.
You'll have a presentation on Wednesday afternoon by Professor Barbarossa about how you can work on this criterion. And he will mention also how these criterion are adapted to the case of having multiple antennas in all terminals, and when you split the resources between the different users under OFDMA. Let me show just one result about how effective is the exchange, and it's related to your question, how effective is the exchange of information under a cooperative game. And here I have on the left the cumulative density function of the bit rate for different macro users associated to this deployment, where we have a macro base station, multiple fabs, some macro users, some femto users, and I'm plotting here in possibly we can concentrate on the red lines here. So this is the cumulative spectral efficiency per user when we are not exchanging any information between femtos. And this is the increase in performance that we obtain when these femtos are coordinated somehow. Right.
Control traffic into account or not?
We are not taking control traffic, but control traffic is very tiny amount.
Okay.
We have checked that we just need to exchange. We can quantize the information exchange between femtos with just a couple of bits.
Okay.
And the performance is good enough. And this is the difference in terms of capacity for the femto users when we are using pricing or exchange of information in terms of between fabs, or we are not. And we have here two very different plots. In red line, we are assuming that the backhaul is providing low capacity, like only 1 bit per second per hertz, which we are considering here 20 megahertz bandwidth. So, or 5 megahertz of bandwidth, I'm not sure. So this should be a backhaul of 5 megahertz, and this backhaul is 15 megahertz. I could possibly. Okay. Anyways, those are backhauls of very different quality, right? We have here a backhaul which is 3 times the bandwidth of the backhaul that they are having the femtos in here. So why this big gap? When femtos have low quality backhaul, they are transmitting lower power, right? They are not fed at high bit rate, so they need to transmit low power. So there is little interference between them. So there is no big gain in exchanging parameters to do coordination of resources. Whereas when femtos have large bandwidth in the backhaul, they are allowed to transmit more power because they can provide more service to the users. They can provide a higher bit rate to the users. There is more interference, and then more is gained by the exchange of parameters for the coordination of the radio resources. So the benefits of coordination in this distributed radio resource management is more important in higher interference scenario. So let me talk now about cooperation, which is the other aspect that the other big trend in managing with interference. And this cooperation can be achieved when you have a backhaul that allows for the exchange of data at the data plane, not at the control plane, or let's say at the control plane and at the data plane, both. And when you have cooperation, then like a new world possibilities is allowed. It's like you may have two femtos here that are serving simultaneously to users, to femto users. When you have that all the messages are known by the two transmitters, we can define a distributed MIMO or cooperative multipoint scheme where you are allowed to do broadcast, MIMO broadcast, with a pool of antennas that is composed of the antennas of the femto1 and the antennas of the femto2. You can also think of using the X channel. The X channel it's kind of a less known concept where transmitter 1 or femto 1 has part of the message that is going to be transmitted to user 1 and part of the message that is going to be transmitted to user 2. And the same for the femto 2. So in both cases, null steering and interference alignment play a key role in doing the precoding scheme. Gains in terms of sum rate, well, are evident if we plot like in a toy example. We have here what is the capacity of sum rate in terms of the signal to interference ratio when we have only coordination, as I showed you before for the game theory case. When we only have coordination, then the sum rate like saturates, because at a certain point there is too much interference and we cannot gain much from adjusting the transmitted powers or adjusting the bandwidth and so on. Whereas if we have the possibility of exchanging information at the data plane and on the control plane, then we gain a lot for the MIMO X channel and we gain much more for the distributed MIMO. And this is also yes.
So you have this dual to broadcast channel, right? So you said that it will saturate at essentially at the high SNR.
Yes.
So what if you just turn off one user and let only one user transmit? So then it will keep on moving up with power, right? Because the optimal solution at that point is to turn off one user and let only one communicate.
Yes, but you are reducing the spectral efficiency, right?
Right. But still, you can gain in the sum rate, right? It won't saturate. That's what I'm saying.
But this is, yeah. I think that this is because this is signal to interference ratio.
Okay. So if you let both of them transmit, then of course it will saturate. But if you turn off one user at the high SNR, of course the other user will keep on gaining with the increase in power, right?
No, well, but I think that what we are plotting here is the signal to interference. So if you turn off one of the users, then
I thought it's power.
Then this value is not increasing because the interference is not increasing. So it saturates to.
Okay.
I think it's a misunderstanding with label.
Yes, yes.
I thought it was power.
Yeah.
Okay. Thanks.
So now this null steering interference alignment are definitely playing a role, and you know that these are techniques that are able to achieve capacity of, well, not capacity, but multiplexing gain a high signal to noise ratio, therefore. But it is also important to achieve high performance at low SNR and at medium SNR. And we need to go beyond the conventional interference alignment or null steering term techniques and move more toward minimum mean square error techniques. And this is something that we have observed in the Freedom Project, is that if you keep in interference alignment, then you have a certain slope, which is precisely the slope of this multiplexing gain for the interference channel or for the X channel. But you can think of minimum mean square error techniques that are achieving at the same time the slope at high signal to noise ratio, and to provide much better performance at low and medium signal to noise ratio that is approaching the capacity of a distributed MIMO bound. What is the benefit of this X channel as compared to distributed MIMO? Because of course we have here a loss of performance. Well, the main difference is that, or the main advantage is that the X channel does not need so much bandwidth at the data plane, because we are not exchanging all the messages between the two fabs. We are just exchanging fraction of messages, right? In here we have in distributed MIMO, all terminals have all messages, whereas in here only a fraction of messages is provided to every fab. Also, the requirements in terms of synchronization is much lower. It is not required to do synchronization at sample level here for the X channel, where it is needed in this distributed MIMO system. Then scalable solutions are needed also for this cooperation that combine cooperation and also coordination, like plugging this X channel or network MIMO into game theory technologies. Now let us see another aspect of a technical challenge in femtocells. Huh? Yes?
So, do you are solving this problem of trying to give some priority to the Mac users, or it's just like dealing with them without giving to the Mac users?
Yeah, you can do that.
Some constraint on like the performance cost of the Mac users and interference. So, what kind of like constraint you are taking here, taking into consideration the Mac user performance?
Well, you can do several things. One is that you can assign more priority to the macro users if you don't want to affect the service given by the macro base station. You can do otherwise. You can exchange coordination messages between the macro and the femtos in a way that the macro is generating like coordination messages, and the femtos take into account those coordination messages, but it is not working the other way around. Like the messages generated by the femtos are not taken into account by the macro, right? So like the macro is working in a more egoistic way, like generating constraints to the femtos, but not taking care of the constraints generated by the femtos. In these previous figures, we had constraints in terms of priorities. Like everyone was like macro and femtos were playing the same game, but there was much higher priority for the macro users than for the femto users. Well, you know, priorities can be plugged in here. And they can be like static or dynamic. You can use here any criterion you want, or proportional fair, or so. Yes, so this priority is included. This meal. Yes. So another technical challenges that is the compatibility or the competition between relays and femtos. For some operators, it might be interesting to deploy relays to provide coverage in poor in areas in indoor or inside buildings where the propagation is poor, especially at a certain penetration of femtos which might be not too dense, like a situation in here where we might think of deploying relays over the cell. And at the same time, we have the coexistence of femtos inside the buildings. But the density of the femtos is not enough to give coverage to all indoor users, so that the operator might be interested in deploying relays close to the building, so that the indoor coverage is improved. So in this situation, we might think of deployment and an allocation of resources which is based on time division, where we have transmissions over a certain period of time from macros to relays, and then from relays to users, and to give another amount of time, fraction of time, for the transmissions between the femtos and the femto users. And this is well possible under the TDD access mode of LTE. So that the allocation of resources, the amount of resources that are provided to the relay transmissions and to the femto transmissions, can be balanced depending on the business plans of the operator. So in the Freedom Project, we have results about that you can check in our website. Yes?
How do you decide whether a given user is a friendly user or not a user? How do you decide that?
Yes, just by proximity.
Okay, so you make it distance dependent.
Yes.
But isn't there
Or just by signal level.
okay, but if you give different priorities, isn't that an issue for optimization? I mean, if a user is just assigned by distance and you give different weights to femto users and macro users, then you should apply those weights to the distance as well for optimization.
Well, in this situation, in the study that we have undergone, we are assuming that there is a previous association between users and femtos, or users and relays. And then this allocation of resources through a parameter alpha is depending on what are the plans of the operator. Like, imagine the operator wants to stimulate that every user is purchasing a femto. Then the operator will allocate lower amount of resources to the transmission from the relays than to the transmission from the femtos. Yes?
What kind of relay devices do you consider? The relays, what are the relays? Is this femto base station can be a relay, for example?
No, relays are just terminals that are communicating with a micro base station through a wireless backhaul, which is an in-band backhaul. So a fraction. These relay terminals. The relay terminals that we're considering here are half duplex terminals. So they are receiving on a certain amount of time. They are receiving from the micro base station, and then in another fraction of time they are transmitting from the relay towards to the macro user.
Have you considered a scenario where a femto can be a relay and there's a two-hop transmission, let's say from the UE to the femto relay and the femto relay to the macro base station?
Yes, this could be well. This scenario could be well. Can be valid because I am considering here a relay station which can be a femto, for instance, that has the possibility to communicate with a macro base station.
Maybe because the femtocell, femto base station, has more context-aware information about the whole environment.
Right.
Say,
Right.
and can
Yes.
take the right opportunistic decision about when to transmit to the macro base station in the separate home.
Right. Yeah. In principle, base station, I agree with you. In principle, femtos are smarter devices than relays. Yeah. I think that this scenario has been considered in BeFEMTO to use femtos as relays. Yeah.
How in terms of industrial development of this, for example,
of this kind of relays, you mean? I'm not sure. I'm not sure. I'm not sure. Maybe any company representative can answer this question.
It's now entering 3GPP.
We have that one that will be.
Yes. All of the study items coming now, it's good for the relay as well. So NEC, which is involved in BeFEMTO as well, and Qualcomm, I believe they have put forward some. Personally, I think beyond 2 hop doesn't make much sense.
Hmm.
We're really talking 1 or 2.
I just want to add, in addition to the 2-hop, at least in the beginning, they also talked about cooperative relays, where the UE can talk to the relay and the macro at the same time.
Yeah.
They didn't get into the 3GPP standards, but I was wondering, in the BeFEMTO, did you look at that kind of configuration?
No, not in freedom. We're just considering very simple forwarding relays. No, decode and forward.
We did, right?
Yeah,
No, we don't.
the COM didn't go to LTE. Yes, it didn't become the part of standardization.
I mean, there was some cooperative studies, but it was not the hardcore type of distributed multi-coding. It was not that.
Yeah, I realize, I mean, the comp with 2 base stations, I mean, they're also, they went for very simple, same data transfer, more of the diversity.
So they were thinking to stand the same technology with relays, but I think this is not because of hardware complication. It will make the user equipment more complicated.
Well, and the gains, I think, you know, I mean, if you just look at the physical layer, the gains might be factor 1.5 and 2, and disappear very quickly as you go up. And the layers, and one of the big advantages of distributed space encoding is that you make a lot of gains on the shadowing actually. And if you go indoors, I think, you know, there is shadowing, but not like that heavy in the sense that, you know, you probably profit in the outdoors.
In fact, the whole relay, the sense I get is that the industry is not really sold on the ultimate benefit of deploying just one more device, you know.
Yeah.
Maybe it's more applicable in open, in outdoor scenario, where you could have a fixed, let's say, coordination plan about the interference,
Mhm.
and maybe you can decide more efficiently about the time of transmission, and which would be the first hop and the second hop.
I can tell you why we didn't use cooperation in here in freedom. This is because we observed that is okay. We did some kind of reeling which is not like the standard reeling. We applied coordinating multipoint to the micro base stations to the relay transmission. So on the first hop, we did coordinating multipoint between these 3 micro base stations to the relays. And this is providing much higher capacity or advantage than using a conventional macro to relay and macro to relay, so on. The fact that we are using cooperative multipoint in the first hop is kind of preventing the use of cooperation.
Yeah, that's a good clarification, because it's not that you are not considering cooperation at all.
Right.
You are considering it in one context as opposed to the other.
Right. Yes. So we are doing cooperation, but only in the first hop. It's not, not like the conventional cooperative relaying as a concept. 5 minutes only. Okay. Thanks. Yeah, I'm going quickly now. So there are a few MAC aspects that need to be considered in the deployment of femtos. One is the distribution of reference signals. This coordination and cooperation requires the estimation of the channel to neighbors, and the fact that these reference signals are colliding. That's a major issue that is under study in LTE. So how to distribute these reference signals. Also femto identification. We know that there is an unlimited number of physical cell identifiers available in LTE, and these need to be associated to femtos in a distributed way. If we want these femtos not to be planned beforehand. So algorithms need to be defined or generated to allocate these PCIs in a self-organizing way. Now for the mobility management. We have many handover scenarios. Every time that we incorporate a new network element, we have a new handover situation. We may have handovers between macro base station and femtocells. We may have handovers between femtocells when we have like open groups for femtocells. We may have vertical handover between femtocells and WiMAX or Wi-Fi terminals, and also well, vertical handover. I think this vertical handover that was for 3G, and also vertical handover within Wi-Fi and LTE coexisting terminals. The big issue in handover is the fact that when we have a dense deployment, we might experience, or the terminal might experience, high number of handovers, an increase of interference, and therefore drop of quality of service. The high number of handovers are present when you have open subscriber groups. The increase of interference is observed when you have closed subscriber groups, but in any case there is a drop of quality of service. So the fact that we have a limited quality backhaul, it's also important to reduce or to control the handover, because the handover messages are going through the backhaul, and the back quality backhaul might affect also the quality of this mobility management. Just to conclude, another aspect is routing optimization. Routing optimization implies that maybe messages between femto users cannot or can be tunneled through some kind of a network device, in the way that we offload the wired core operator of the network. So we might think of protocols or mechanisms so that femtos are communicating to each other through some kind of gateways, and offload the network of the operator in a whole. And this is concluding my presentation. Let me remind you that part of the work that I showed has been performed in the Freedom Project, a project that started in 2010 and just concluded December last year. And I would like to acknowledge the work of many of the partners in the project. Some of the achievements can be freely downloaded from our website. Among them, we have 12 reports available. All of them have been already uploaded. We have 5 contributions to LTE Run 1 and Run 3, especially in the definition of the X2 interface, in definition of scenarios, sensitive scenarios, also in the coexistence of relays and femtocells. And we have also generated 4 patents to the US Patent Office and European Patent Office. And this concludes my presentation. I'll leave this slide so that you can get the link to our website, and I'll be more than happy to answer your questions.
So are there any more questions to the discussion we already had?
Yeah, just a quick one. Regarding the 5 contributions to Run 1 and Run 3, I would like to know what's the nature of these contributions? Are there change requests to technical specifications, technical reports? What's the actual form of these contributions? Thank you.
I cannot tell you exactly how many of them there are. We have technical modifications, and we have I could tell you, I can check that and tell you afterwards if you want. Yeah.
Okay, if not, Josep is still around for a while, so thank you very much, Josep, for the overview of the week, because we're going to be going point by point throughout all these days. So in the afternoon, we're going to have an interesting complementary presentation to Thierry's one on the Femto Forum's view, etc., on the evolution of femtocells. And then in the last presentation today is very important also for the reminder of the week, because it gives us the 3GPP architecture overview, which will help us to understand all the constituents we will be discussing throughout all these days. So thank you very much again, Josep. So
thank you.
Thank you. Coming now to some logistical issues. So we're going for lunch now, and today's the first time we'll go there. So I'm gonna take, I hope I get some help from some CTTC people.